Okay, so you can't really talk about AI and art without at least mentioning DeepDream, right? So DeepDream was actually started as a blog post from a bunch of Google engineers back in 2015. So Mordvintsev et al., if you look at the course webpage, you can see there's a link to the blog post that started it all. So Inceptionism, going deeper into neural networks. But this is what everyone ended up calling DeepDream, okay? So DeepDream basically fell out of a huge neural net called Inception that was not designed for making art. I guess that actually this is styled as one word. I just kind of said it as two words here by mistake. So DeepDream basically was based on this huge network called Inception, which some of you may have heard of. And Inception was really an image classification network. Like so many of the early deep learning networks, it was made to work well on classification tasks, right? And so remember that the way that in a very sketchy way, a classification deep network works is that I have an image and I put through a bunch of layers, and at the end, ... I end up with a decision or a classification. And the general idea behind a deep network is that what's happening at low levels of the network, the lower layers, is that I'm picking up kind of like, low-level features, right? So maybe the earliest parts of the network are picking up on kind of like these old school image processing features, lines at different angles and blobs and circles and stuff like that. And then by the time that I kind of get to the middle layer of the network, suppose I'm training this on, cats and dogs, right? So maybe in the middle layer of the network, I've got, faces or features of faces. And at the end of the network, I have, whole animals. Like the layer is responding to this high-level stuff. So generally, this is a very sketchy explanation, but more or less, low layers are like kind of basic image processing stuff, and I kind of put those features together into more and more complex, collections of features, okay? And so the clever idea of DeepDream was to take the pre-trained network, and instead of using it for classification, the idea was to say, okay, I'm going to put an input image in to the network, and then I'm going to choose one of these layers, or even maybe a specific neuron in one of these layers, and I'm going to do gradient ascent on the input image to try to maximize the activation of that layer or that neuron, right? And the effect is that you're really amplifying, turning up the knob of what that layer sees, okay? And so the result of this was to get all these kinds of trippy effects, right? So let me write that down. So the idea was to, choose a layer, and then do gradient descent to, maximize, and maybe make it clear that this is a gradient descent on the input image, right? So it's like I'm trying to figure out what input image will cause the layer to respond as much as possible, right? So I'm basically trying to maximize the output of that layer. So kind of it's amplifying what it kind of responds to or sees. And so the idea would be that if I enhance the lower layers, the result is that you get basically, kind of cool lines and geometry, right? And if I enhance the higher layers, what comes out is you kind of start to do these crazy hallucinations. You can hallucinate, whatever you want, dogs, cats, fish, birds. kind of a word for this is called, I'm not sure how to pronounce it, pareidolia, right? This is kind of like the phenomenon that means that you as humans will see kind of faces and stuff in, like, you look at an electrical outlet, it looks like two eyes and a mouth, right? So it's kind of like this is like a deep learning version of amplifying this. And so let me just kind of show you instead of telling you what this looks like. So here are some of the classic DeepDream examples, right? So here, this is like taking the input image, and then you kind of do gradient descent on this image to amplify the output of something at the low layers, so you get these kinds of cool, stylized like lines and curves, right? It's kind of like turning up the geometry, right? But then instead, if I were to take an image and I were to amplify the higher layers, then you can see that I'm turning up the hallucinatory aspect of it, right? So you can see like this image stream here, something looks like there's some sort of like a dog or something in here. And this kind of coincidence of a tree and something else turns into some sort of bird. And then down here in the rapids, we have like dog faces and stuff like that, right? So when this came out, people just were crazy about playing with it, right? And so, for example, if you feed in just like noise to the image instead of just a natural image, you can get all these kind of like really trippy effects, right? So like you get stuff like this, these weird spirally towers and stuff like that. This is kind of like the thing that you imagine if someone's having an LSD trip, or you got some sort of like, fluorescent poster in your college dorm room, right? So it would be used to kind of generate these like really cool, weird looking things. And so when DeepDream came out, people just loved to play with it. So you get eyeballs, and these kind of maybe look like maybe the snouts of dogs and stuff like that. And here's a video that I found called Grocery Trip by a YouTube channel called Poof. I don't know why it's not playing. Why wouldn't it play? All right. Well, let's go to the YouTube. Okay, browser. What happened to my... hey, look at what fell out of this, inception network, right? They kind of noticed that certain neurons in certain layers responded to certain classes of objects, and that led them to say, well, what would happen if we crank this up, right? And so you can look at the original blog post for more information on this, right? And of course, those kinds of effects that you saw were produced by kind of like, successively, feeding video in, or you can kind of keep on zooming in the image to get these kind of more and more psychedelic effects and animations and so on. So, but let me pause. Did anyone hear about DeepDream when it came out back in the day? No? All right, well, I'm teaching most of you something for the first time. All right. Okay, so DeepDream was one thing, right? And so around the same time was a lot of work on what was called neural style transfer, okay? And so I wouldn't say it's that related to DeepDream other than that it's similarly related to taking activations at different layers of a network. So around the same time, there was a lot of interest in what was called, or what is called, neural style transfer. And so this is basically kind of like a new way of making an input image X appear to be in the style of some different style Y, okay? And so in a way, it had the same goal as back in the day, I told you that paper called image analogies, right? So making a photograph look like it's a Van Gogh painting, right? It's like doing that, but this is like kind of one of the early deep learning-based methods of doing that, right? So the idea was to make an input image X look like some other style Y. And so the key paper in this field that kicked it all off was by Gaddis in CVPR 2016. So again, not that long ago, by my standards at least. And so the key idea was to basically, we kind of have a goal of creating this stylized image I. So this is what we want to create, that renders a what we call the content image or the source image. Let's call that I sub C in the style of, kind of like a style or target image. Let's call that I sub S. And the kind of natural loss function for this problem is basically to say, the optimal I that I create is what I get by minimizing over all my possible outputs a loss of the form, I've got some sort of a loss function that says what is the, content loss, right? This is like saying how similar is the stylized image to the original, source image. And then I've got a term that is like a style loss. We call this style loss. And typically, these alpha and beta are tuning parameters that weight how serious I am about, which of these things is more important. And typically, alpha over beta is much less than 1, right? Meaning that alpha is much smaller than beta. So I'm really prioritizing the style loss over the content loss, okay? And of course, I can tune these things, that I'll show you in a second, to kind of, affect how conformal the resulting image is to the original picture, okay? So the reason I'm kind of putting this in the same lecture as DeepDream is because it has a similar flavor, the original paper, of saying that, what I want to do is I want to compute these losses at different levels of a neural network that was trained for some other purpose, right? So the original paper, used the VGG network, which was used for classification, which has 19 layers. And so kind of what they were doing is they were evaluating these style and content losses in different layers of this big object classification network, okay? And so the similar idea from DeepDream is that, the lower layers encode kind of like, circles and lines and low-level image processing stuff, and the higher layers encode more like features that control what's actually going on in the content of the image, right? So in some sense, it kind of makes sense that this term here is related to what's going on at high levels of the network, right? So basically, for the content loss, the observation is that, higher layers in the network capture basically, kind of like objects and their arrangements without being so picky about actual pixel values, right? So it's kind of like big picture of, does this image contain this stuff, right? So the content loss kind of makes sense as something along this line, right? I have my source image and my desired image. So looks something like this. What I'm going to do is I'm going to sum up over all the layers. This is basically, which content layers to use. Generally, higher ones. And what I'm summing up is basically the differences in feature activations of each of these layers, right? So it's like saying I look at the sum of the features at layer L in the original image versus the features at layer L in the image that I'm trying to create. So basically, this is like the difference in feature representations at layer L. And of course, there's a lot of hand tuning to figure out what layers are the right ones to use for the right content loss, okay? So that's pretty straightforward, right? And again, this kind of goes back also, just as a side note, to remember we were talking about how, for perceptual image similarity, we generally, got better results by looking at the outputs of different layers of a neural network. This is kind of similar to that, right? When we talked about, perceptual image similarity, this is kind of coming out of that work as well. So content loss is pretty straightforward because, I have a source image that is a photograph usually, and I'm trying to compare it to what I got. So it's kind of natural to do a one-to-one comparison, right? The style loss is harder though, right? So if I say, okay, I want you to make this photograph look like it's a Van Gogh picture, does that mean that I want to take elements from the Van Gogh picture and put it into the resulting image? Not really, right? What I want to do is I want to kind of capture the general feeling of the swirliness and the saturated colors and all that, right? So I don't necessarily want to do quite the same thing for the style loss. So one observation of the paper that, again, was a key thing that moved the field forward was the idea of what should be the style loss. So the style loss is basically, instead of trying to match features exactly, the observation was to try to get correlations in the feature maps to be similar, right? So the idea, let me write down first, is that we want feature map correlations in I and IS to be similar. So this comes from an old idea in, so first of all, let me just show you kind of like before we go on what it is we're going to be doing, right? So the image at the upper left is a photograph of these nice houses on a canal, right? And I can provide, different input images of different artworks in this case, and then the resulting style transferred images is the original photograph rendered in the style of Van Gogh or Munch or whatever, right? And so, and you can see that, in some cases, like this is a fairly faithful rendition, although it's got some Van Gogh, moons and stars and stuff. This has kind of inherited the wavy sky from this picture. And this, you almost kind of have to squint to see where the original buildings are in this, kind of abstract art version. But you can see them if you think about it, right? You can kind of make out, for example, that there's this yellow building on the right-hand side, right? And so here's an illustration, and I really like this blog by Peter Ruprecht. So if I go back to my browser for a second, if you want to learn more about this, I've linked in the web page to this Understanding Style Transfer blog, which I think is actually quite good in terms of trying to explain like why does this work. It's particularly the style loss, I think, is the part that's hard to understand, right? So here's some pictures from his blog post, right? This is kind of like saying, okay, let's suppose that we take two classes of images, clouds and pictures of concrete, okay? And now I'm looking at basically feature maps at different layers of this big network, okay? What I can see is that the feature maps that kind of correspond to what I put in these red boxes for these two concrete images look very similar to each other, right? So regardless of the actual feature values themselves, what I can say about this is that feature map 4 and feature map 5 for concrete images appear to be positively correlated, right? In the sense that, even though the features themselves between concrete 1 and concrete 2 are not the same, I can say that for a concrete image, I expect there to be high correlation between what I see in number 4 and what I see in number 5, right? And conversely, that's not going to be the case for these feature maps of these cloud images, right? So in some sense, that signature of 4 and 5 is something that's really discriminating for the concrete images, right? And conversely, there's kind of like no correlation or maybe negative correlation between feature map 5 and feature map 15, right? So what we do is we make a matrix of, for all the features at a given layer, how similar are they? How correlated are they? Okay? And so there's a picture here that I think is good for that. So kind of what we do is say, okay, suppose we look at lots and lots of cloud images, okay? And I think about, for a given layer, I put all the features on this axis, and on this axis, I look how correlated are these feature maps, right? I can see that all the cloud images kind of have a similar look, right? In some sense, this is like saying this is what kind of characterizes the cloud style, right? And so that's a good sign, right? That all the cloud images kind of look the same, and they also look very different from all the concrete images. There's maybe a little bit less kind of like, you know, overall similarity in the concrete images, but clearly they're much different than clouds, right? So kind of what I'm trying to do is I'm trying to force the output image to have a similar look to whatever this looks like for my style image, right? So let me try and write that down a little bit more concisely here. So, and again, this, you know, this kind of comes from, you know, back in the day, there was a lot of work on like texture synthesis, right? So supposing that I wanted to synthesize realistic clouds or concrete from scratch, right? You know, there were lots of observations about, you know, how do I kind of characterize what separates one texture from another texture from an image processing point of view, right? So the idea is that human perception of texture similarity is related to kind of joint statistics or co-occurrences of different features. So it's not just saying like, you know, is feature X present, but is feature X present at the same time that feature Y is present, right? These kinds of correlations. And so how am I going to kind of capture this? Well, this idea of these matrices, right? So if I go back to this kind of picture with the matrices, these are what are called Gram matrices. And that was what Gaddis et al. Kind of used as the basis for their style loss, right? So, you know, we capture this correlation using what are called Gram matrices, which is really nothing more than saying, you know, if I have, you know, feature map, let's call them I and J in layer L, then the ijth entry of the Gram matrix is just the dot product of feature I and feature J. And so it's like I have one matrix per layer of the network. And that dimensionality of the matrix is how many features there are or how many channels there are in the network, right? Or in the layer. So the overall style loss is along the lines of saying I have a loss for the style between my target style and the image I'm generating. Again, I have a sum over the layers that I'm going to use for style. And instead of comparing features directly, I'm comparing the Gram matrix of the features at layer L of the input style and the Gram matrix here. So what I'm doing here is I'm comparing the Gram matrices at a set of desired layers. And so what they did in practice for this paper was they basically used 5 layers and averaged the style loss over those different levels of the network. And they were kind of spread out across the network. And then to actually generate the image, right, kind of what we do is we start with a noise image, kind of similar to the way that like a diffusion or GAN works. And then we do gradient descent on the image pixels to minimize this kind of sum of the content and style loss, right? So let me just say that to generate the image itself, so to actually generate image, what we do is we start with a noise image, the same size that we want to create, and then we do gradient descent on this kind of like content plus style loss. And then kind of similar to other methods, like again, you're probably familiar with if you've used Midjourney or Stable Diffusion, what happens if you choose different input noise images is you get slightly different outputs, right? So in some sense, this is an early version of this kind of idea of getting a bunch of similar renditions of a query, right? And you kind of choose the one that you like, right? So, different inputs for the noise lead to slightly different output image variations. And so let's take a look at some examples of that. So for example, here on the left-hand side, you can see that what we get are, if all I do is change the noise image that I put in and then do gradient descent from that position, changing nothing else, I get 4 slightly different versions of a Van Gogh-based version of this picture, right? So, it would be hard to say exactly what the differences between these things were, but like, the stars in the sky are in different positions and, there are different reflections in the water and so on. And then also, you have to pay careful attention, and this was, I think, originally kind of manually tuned a little bit to figure out what are the right layers that you should use to get good style transfer, right? So for example, an observation was that on the, if this is my original image, and then the lower left-hand corner here is the kind of target image, if I use this convolutional layer, it kind of looks like I'm just kind of using some sort of a, Instagram image filter on top of the original photograph. It doesn't seem like the result here is really sticking very well to the source. It looks kind of just like a cheesy filter, right? Whereas if I used another layer, further down the network, the resulting image really does look a little bit more painterly, a little more stylized. Things are more wobbly. There's less faithfulness to the original image, right? So there's a little bit of an art to choosing what is the right set of layers to use for your style loss. And then just like in other systems, if you kind of turn the knob for the balance between style loss and content loss, you can kind of see that the lower right-hand image is on the more faithful side, to the content, right? So I want to make, so here you can merely make out the images of the buildings and so on, right? Whereas if I really amp up the knob on the style, I kind of lose an interpretation of where the original buildings and so on were, right? So I can barely tell that these are supposed to be images of buildings in the first place. And as I kind of increase the fidelity on the content, I get more and more faithful images, right? So again, it's the user's choice to decide how should I move these knobs around to get what I want, right? Okay. So let me pause and ask. Any questions or comments about this? Yes?
So for, as long as we choose more than like 2 layers, like the lower resolution, the higher, I mean the lower layer will always have like higher weight in terms of the loss, right? Because the spatial size.
Right. So the question is like if I choose lower levels and I have the same weight, then I effectively am weighing those more. Is that what you're saying? Yeah, that's a good question. And actually, I'm not exactly sure in the original paper whether or not they account for that issue. Let's just see here for a second. So, well, here this is like saying they weight these equally, the layers. And it looks like the ratio is also the same for the style versus content loss in all these cases, right? Yeah, so that's a good question, actually. I'm not exactly sure why it doesn't act to weight the lower layers effectively more, right? Unless there's something in here that I'm not remembering about exactly how that works. So good question that I'm not exactly sure the answer to, but it seems like it makes sense from what you said, right? I'm sorry, you couldn't even see what I was looking at, but that's all right. I wasn't finding anything interesting in the paper anyway. Okay. Other questions or comments? Yep.
So in DeepDream models, can you control the dreamy objects?
Can I control the what?
The dreamy objects, the artistic objects that are like, for example, the picture of the dog. Can you control the level or the intensity of the colors and everything?
I don't think that there's a lot of control on the style here, right? So for example, I don't think there's like a knob that says in these Van Gogh images, I want to make it swirlier or I want to make there more stars or something like that. I don't think that you can really do that, right? So I don't think you can in some sense, kind of what you're saying is, can you amplify the style, right? Now that I think about it, there may be a way of thinking about could you combine this with a deep dreamish kind of thing to say, okay, make this as Van Gogh as you can, just turn it all the way up, right? I can imagine that you could do that, but I don't think that they were doing that in these papers. But I think that there's a path to doing that. That's an interesting idea. Yeah. Other questions or comments? Okay, so as is the norm, this this style transfer paper, I mean, people have been talking about this kind of idea of making images look like paintings, back to Hertzman in 2000 and before. But this set off a whole bunch of excitement in terms of specifically this kind of neural style transfer, right? So, this basically immediately set off a bunch of refinements and extensions. And so the first observation was that the original paper was very slow for its time, right? So for example, it could take minutes to almost an hour to generate one of these style images, which is obviously way too slow, right? So later refinements made the process virtually interactive, right? Which is great, even real time, right? And so one of the things that was a key step was, by who's the author here? I'm looking for it. Ulyanov et al. In CVPR 2017, so kind of like the next year, instead of doing this optimization, they instead developed a feed-forward neural network to solve the same problem, right? So basically, feed-forward neural net to solve the same problem, which was kind of limited by the fact that, this was like a single style only, right? So you basically had a network that was customized for Van Gogh, for example, right? But it made things like 3 orders of magnitude faster. So if you only really cared about a certain kind of style, then it made sense just to train a custom model for that. And basically, I think that the loss function was more or less the same, right? And a key reason to make this work, and again, this is something that, again, to me as a deep learning novice, it's one of these things where it's like, why would this make any difference? But it turns out that a lot of the innovations in the style transfer space have to come with, have to do with a very kind of low level question about how features in the network are normalized, right? So, the key innovation from this paper was that, you may know from neural networks batch norm, right? Batch normalization. So batch normalization we talked about before is like saying, I take a batch of features, I subtract off their mean, I divide by their standard deviation, and then I multiply that by some new, scale and shift to change the variance of the batch and the mean of the batch, right? So, this is kind of done all the time in neural networks, and the kind of observation from this Ulyanov paper was instead, to get good results using basically, what's called instance normalization, which is almost like just saying a batch size of 1. that normalization difference, made a big impact in terms of apparently both the speed in terms of convergence, but also the kind of perceptual quality of the results. And so there was another innovation by Dumoulin kind of around the same time where they proposed that you could learn this gamma and beta for a fixed set of styles and kind of train it all in the same network, right? So instead of just having a single style network, you could have like I think that they had a 32 style network that was learning the gamma and the beta for each of these 32 styles separately, right? And so that was also an innovation. And then there was a further one that, I think I mentioned this in the context of, I think we talked about this in StyleGAN back in the day, but there was another paper, again, this was in ICCV 2017 by Huang and Belongi. Where the innovation of this paper was to use yet a different kind of normalization called adaptive instance normalization. So basically, it's kind of like trying to align the input mean invariance to that of an output, right? So the normalization there, if I'm trying to normalize x to y, is just like saying I take, I normalize x, and I make the mean invariance match whatever y is, right? And so if I were to do a possibly confusing sketch of what this works, kind of the idea was, in this paper, I have a content image and I have a style image. I feed these into an encoder. I do this normalization. And then that goes into, one branch of this goes into a decoder. This produces a stylized image. So far here, the style image isn't playing a big role. So it's kind of like saying that this part here is producing the style loss. And then this part here trying to figure out how this works here. Is producing the content loss. Or maybe it's not plus, it's just a box, sorry. And then these two things are added together to produce the total loss. So the idea is that they trained this over a lot of style and content examples so that they can learn how to apply this to any style, and it works in real time. So kind of like the idea was that we went from the original paper was a single input style, single input content that you could then take a few minutes to make this nice image. Then we went to a faster network that could only do it with one content, or one style, sorry. Then we went to a network that could do it with like 32 styles, and then we made a network that could do it from any, kind of pair of content and styles. Of course, the trick is how do you kind of like, get these input images to work with, and then also how you compare the results, right? So it's a very subjective question about like, do the results look good or not? So, and of course, after looking at a bunch of style transfer, papers, you see a lot of like figures, comparative figures like this, right? Where, honestly, I don't know why Brad Pitt is always the poster child for style transfer, but you see Brad Pitt, in many different styles if you read style transfer papers. I think, again, because this probably came from the Stylabay data set, right? And so, for example, the rightmost column is the original paper, which I think is still held to be kind of like the gold standard in terms of the images look good, right? But then as you kind of go, like the leftmost one is the Ulyanov paper trained on a specific style, and then the third column is this paper by Huang and Belongi kind of showing what the result is, right? So, I mean, if you were to just look at the matrix of the 4x4 pictures on the right, and you ask one which is the best, or which is the best one in each row, I think that's a very human interpretation of like which one looks good, right? And I will also say that, I mean, not to criticize any of this work because it's really cool, but at the same time, you know, it's not really obvious to me like that this is something that people are wanting to use, right? Like maybe sometimes you'll see like a stylized profile picture or something like that. For a while it was popular. There was an app called Prisma, which I never used, that was kind of like a style transfer built into an app, right? I will also say that, you know, for the most part, and again, this is a very personal opinion, you know, you're not going to get like Spider-Verse level effects from a neural style transfer algorithm, right? And part of the reason is that even though these algorithms kind of can look painterly in a way, at the same time, there isn't really any sort of sense of, you know, strokes of paint or a medium of like trying to emulate watercolor or oil painting or anything like that. You know, there's you know, not necessarily any real enforced coherence to the video version of the output, right? So, you know, when you look at how people are rendering those kinds of super stylized things like, you know, Spider-Verse and the new Teenage Mutant Ninja Turtles movie that just came out, right? That's going to be a whole different pipeline than neural style transfer, right? But nonetheless, I mean, it was a pretty cool result, and I definitely wanted to include this work in the context of, you know, what we're talking about for computational creativity, right? You can't talk about this stuff without talking about both DeepDream and style transfer. All right, so let me pause to ask questions or comments about this. I mean, I will say that I think that, you know, by now this is a pretty mature thing, so you might think about, again, as you go into your projects, you know, like, could you use some sort of style transfer, you know, either visual style transfer. I believe there was a project that was kind of proposing to use similar style transfer ideas. You could imagine that you could extend similar ideas to, like, you know, take a video person dancing and then turn into someone who is dancing in a certain style, right? So kind of like, is there a way to transfer, you know, similar features from one domain to the other, even if it's not visual, right? I think that's kind of an interesting idea. Okay. All right, so questions or comments about the technical stuff? Yes?
I guess one thing I noticed about these results, especially the Radke headline, is that they very superficially look like they're capturing style, but they're really nowhere close. Like on the Picasso, all the lines are very straight,
Yeah.
and it doesn't do that at all with the picture.
Yeah, I mean, I think that, you know, that's the thing, right, is that, you know, you would never say that any of these look like the Picasso, right? I mean, there's kind of a sense of the tone is similar, maybe some of the kind of like hatching is kind of similar, but yeah, I totally agree, right?
Yeah, were there or are there efforts today to try and capture the higher level features of a Picasso, or at least that Picasso?
I mean, I haven't seen anything that is close to making like Picasso-esque versions of Brad Pitt. Although one thing I will say actually is that someone on the Discord posted this New York Times article from last week, was that you? About like basically they trained probably a diffusion model on this one artist's body of work, right? And then they started to generate versions of things that looked like their work, right? So that would be something that would be along that line of like trying to make, you know, but I'm not even sure with that. Like if you fed a network with lots of Picasso portraits, would it generate these faces with like big eyes and big noses and so on? I'm not sure that it would necessarily.
Actually, in that article, it was the artist himself.
Yes, right. Yeah, so the artist himself was involved and was playing with it, right? And that was actually one of the kind of, you know, it's in a way it's supposed to be kind of like a, you know, taking your art back from the deep networks, right? You know, so yeah, I mean, with all this stuff, like they're definitely using, you know, paintings that are in the public domain, and they're using pictures that are in the public domain, right? You know, I think that probably, you know, not a lot of artists would be super jazzed about necessarily seeing their work in these kinds of papers, right? So I know one friend of mine, you know, had a really nice result with the work of a living artist who basically said, no, maybe that picture was shown in like talks, seminar talks and so on, but it could never be included in a published paper, right? Or anywhere that was on record just because the artist didn't approve of it, right? So, yeah, and I don't blame them, right? I mean, there's no reason why they should consent to their work being used to kind of make things that mimic their work, right? That's a kind of a sketchy thing, yeah. Yeah.
So still on this like Picasso graphics
Yeah.
transformation, because there were like a series of like learning model called offsetNet, like
Mhm.
they try to learn this like certain offset. For example, like this is for this graphic is like really like a photo, right?
Mhm.
And then for this Picasso it's kind of like abstracted, a bit of like exaggerated.
Mhm.
So if we choose like a model that just try to learn this like offset from
Hmm.
the photorealistic world to the like bit of like Picasso style
Hmm.
thing, maybe this can help to generate this like Picasso
Yeah.
style.
Could be. So offsetNet was what you're saying. Yeah. Could be. I mean, was it made for like artistic or aesthetic applications, or was it made for something else? Made for something else, right? Yeah, it's an interesting idea. So offsetNet, we'll take a look at that. I mean, also, I think that, in addition to the deep subjectivity, like, and I think, again, if you look at, I think that Aaron, who's going to talk to us next week, there's a lot of subjectivity in terms of like, even in these papers where these are evaluated, if you were to ask, a bunch of mechanical Turkers, which one do you like better, or is this closer to this style, that style, they're still just not, looking at it from an art point of view, right? Like, I don't think that there's anything of these 4 images that is like a great rendition of Picasso, right? You could argue whether one is better, closer than the other one, but maybe on an absolute scale, it's pretty low still. I think the most successful ones are probably the, less photographic ones, right? Like, I think that the second row and the fourth row are not bad. And they're kind of cool looking. But again, it's kind of like, what are you learning, right? Would the person who painted this lower left-hand image paint the Golden Gate Bridge like this, or would they paint it in some sort of totally different abstract way, right? Like, you can see that their style, the person is not photorealistic, so why should the bridge be photorealistic? And they do kind of wiggle this around, at least in the Gaddis result, right? But it's still not, you wouldn't know, there's no right answer here, right? But there are probably a bunch of like wrong answers, right? So yeah, so it's interesting stuff. And so, yes, there are a couple of nice neural style transfer survey papers if you're interested in this field to kind of read about the big picture of how this stuff works. And in general, I think it's nice to talk about just in terms of like all this kind of comes from just playing with the activations of deep networks at different scales. And in a way, it kind of falls out of networks that were not designed to do this at all, which is kind of interesting, I think. Okay, so I'm going to stop there on this.